Hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video. All math basic course, and as always, it is an honor and a privilege to be serving you today as it is every day here in my virtual classroom. Step on inside as we jump into section 4.5 in the Big Ideas Math Integrated Math 3 textbook on performing function operations. Now, although this is in chapter 4 and we get to use things in chapter 4, the stuff that we hear in this section is not limited to things that are just chapter 4 based. So they might throw in a lot of things that are radical based, but this can apply to any kinds of functions that we have, so keep that in mind. Strap down or look down in the description section down below and download the PDF to this thing, or find the timestamps, or go to the playlist and find other things that you'd like to alongside this section. We're gonna have a problem set that is shorter. I believe it's in the 20s. Let's take a look. Up to number 27, but who knows? It's shorter in quantity, maybe not necessarily in duration. So without further ado, we'll go ahead and get started with the lecture portion, and then the problem set comes after. We're going to add, subtract, multiply, and divide functions, and that's pretty much what it is. Now the notation will look a little bit tricky. I guess scientific notation will be involved. I don't yet know where, probably in division problems. You have learned how to add, subtract, multiply, and divide polynomial expressions, right? Combine like terms for these, like distribution of this one, and like long division, synthetic division, things like that. They can also be defined for functions. All right, so there is a notation that they have for all of these. Let f and g be any two functions. A new function can be defined by performing any of the four basic operations on f and g. Now, here is f of x plus g of x adding two functions. There's a shorthand notation to it that looks like this: f plus g of x. That's what this says. It does not say, and I need to repeat this because I'll stress this to my classes and they'll still get it wrong, and I get upset. It does not say f plus g times x. This is not, they have a like distribution into functions, but this is not multiplication. This is not an x that's multiplying in here. This is just a shorthand way of them writing add these two functions together with respect to the same input. That's all that it means. F plus g of x is f of x plus g of x, not f of x times, not f times x plus g times x. We should know how that stuff works. Anyway, so straightforward. If you have an f of x that's 5x and a g of x that's x plus 2, let's add 5x with x plus 2 and get 6x plus 2. You're literally just doing this function plus the other function. But the shorthand appearance of it might confuse people. F minus g of x is f of x minus g of x, so you subtract them. Notice that they're putting x plus 2 in parentheses here because it's a substitution of your function. You would distribute the negative combined like terms and go to work. That's no different on anything we would have done before. It's just a reminder that when you subtract, or anything, even multiplication, that you wrap them around parentheses, you quantify them in a certain way so it's the entirety of the function and not just the first term or something like that. So f times g of x is here, and again, shorthand. Do I prefer this look? Absolutely. Do I prefer that look? Absolutely not. And every time I have this, I'll take it and write it like that even. So f times g of x is f of x times g of x, so a distribution there, and f over g of x is this. Now, they did not apply long division on this for whatever reason, uncertain. I know that our next, I don't know if it's next chapter or the one after, it's on rational functions, and we're going to be doing things with things like this. They'll be bigger polynomials, but we'll be doing more things like this. So I'm curious to see what they do on the division realm. If it's not just dividing two monomials to simplify, when it's binomials or quadratics or something, maybe they won't include a lot of them. Now, something about this one that's going to be very important, and they haven't shown it yet. I think they're talking about domains right here. I want to bring up the domain in this part right here. You can't divide by 0. So you have to make sure that x, for example, isn't negative 2. So there are things like that that we're going to have to be very careful of on division questions. Okay, the domains of the sum, difference, products, and quotient functions consist of the x values that are in the domains of both f and g. Additionally, the domain of the quotient does not include x values for which g of x equals 0. There it is right there. You cannot have negative 2 on this one. X cannot equal negative 2 because then you divide by 0, and that's not allowed. All right, adding two functions. Here's another example. Here's f of x, here's g of x. They're both radicals, radical expressions. They said find f plus g of x and state the domain. Then evaluate the sum when x equals 4. So f plus g of x, they combine like terms, this plus that. They get negative 7 root x. The domain is x is greater than or equal to 0. That's allowed for square roots, right? It depends on your kind of function. They're both square roots, so x is greater than or equal to 0. I can't find where they wrote the domain. They have the same domain. Oh, all non-negative real numbers. There it is. I was looking for an inequality. Now they say substitute 4 for x in here. So we can do it straight into the newly combined one instead of the one that's separated. And negative 7 times square root of 4 is negative 7 times 2, which is square root of, or which is negative 14. if you can apply a combination of functions and make them graphable like that. You can make two functions and say y1 plus y2, and then they'll add together to become of it, and there's a double check of it. I'm probably not going to use second method unless it seems to make more sense to do so. I tend to prefer algebra personally. All right, subtracting two functions. Let's move over. Subtracting two functions, more of the same. We got this guy minus this guy. They're going to be asked for f minus g of x. So this guy minus that guy. Keep in mind you want to use parentheses to start off. They didn't write parentheses around f of x. It's not a requirement, but it's that minus that. When you combine like terms, you get this cubic polynomial here. And then they say do x, all real number domain, and substitute -2 for x into there, and you will apparently get 3. So not much compared to what we've done in the past. We've done all these things before. We're just using the new notation to then write out what the new thing is. Multiplying two functions, we got this times this. Keep in mind if they were binomials, trinomials, we do full distribution. But we have to do x squared times the square root of x. Looks like they're going to find a way to combine it. Instead of writing x squared root x, which for me is completely valid and completely okay. I don't know why they'd simplify here necessarily. But 1/2 is also, 2 plus 1/2 is also 4 halves plus 2 halves, which is 5 halves. I mean, if you ask me, I prefer this over that. I'll probably kind of show it indicators of both, but here's the multiplication of it. Domain is still based off this. Hold on, I'm reading the bottom to see which one I want to say, but based off this here, x has to be greater than or equal to 0. Doesn't matter that this one's all real numbers. Okay, if this one has a restriction, then you're still restricted. You still can't take square roots of negatives. Even if it's written in this form, you still can't take square roots of negatives. So the domain of this consists of all non-negative real numbers. Once again, x is greater than or equal to 0 in that situation. And then if you graph that whole thing together, you're going to see the graph looks like this. It looks like it doesn't go negative. So graphs have their purpose. Substitute 9 in here, you get 243. And then dividing two functions. So it looks like here we have two monomials, 6x over x to the 3/4. I definitely want to simplify this one because that's an irrational denominator. Looks like instead of rationalizing, they go straight to the subtraction of your two exponents. X to the first divided by x to the 3/4. 1 minus 3/4 is 1/4. You could write it like that, or 6 times the 4th root of x. Okay. Domain here, once again, non-negative numbers. X also can't equal 0. When you look at the original one right here, if you plug in 0 for x, you'd be dividing by 0, which is not allowed. So now the domain is not just greater than or equal to 0, but greater than 0. All positive numbers only. No non-negatives, and not 0 either. Let's see how they wrote it. The domain is restricted to all positive real numbers. So there's your domain. I'm going to write them as, as inequalities. So anyway, you substitute 16 as requested for this question here. 4th root of 16 is 2. 6 times 2 is 12. So very straightforward examples as a whole. We just got to make sure to identify the domain. Let's perform using technology. This time, I guess graphing calculator is a required bit. We're going to have to follow along with this format. Y1 and Y2 are features on our graphing calculator somewhere. I have to find where the buttons are as well. I know where L1 and L2 are. I'm going to find Y1 and Y2 eventually. I know that they're somewhere there. Anyway, so we have two functions, square root of x, square root of 9 minus x squared. This is a radical, right, function, a general half parabola. This one's half a circle. But when you add them together, it becomes, I don't know, whatever. We get to add them, subtract them, multiply them, and divide them. And this is where you get to go straight shorthand for these things. And you get to evaluate when x equals 2. Now that I realize that's how you can substitute something in there very quickly outside of use of a table, you can put parentheses around it, which is nice. So y1 and parentheses 2 does not mean take your equation and multiply by 2. It means substitute 2 into your equation. So evaluate all of these when x equals 2, use the calculator. We get some rounded values because they're, irrational values. And we get those answers there for all of them. So y1 plus, f plus g of 2 is 3.65 rounded. F minus g of 2 is that one, etc., etc. So let me find those on the calculator. I know that y1 and y2 exist somewhere here. I have to clear out things from my last video that I just did a bit ago. So here are y1 and y2 like that, but they exist in... I think it's these. Okay, so it's vars, y-vars, and function. So that's where y1, y2, etc. are. So if I had an equation for there, let's just say x plus 2. So let's go to quit out. go to vars, y vars, and function, and y1. If I wanted to substitute 4 into there, I should get 6, right? 4 plus 2 is 6. Or if I did, yeah. So that's an example of that, substituting that in. Awesome. So we have that all set up, ready to go. Cool. Okay. Whoops. Now that I remember where that went. Solving a real life problem. For a white rhino, heart rate R in beats per minute and lifespan S in minutes are related to body mass M in kilograms. So I don't have S. Oh, they're two different functions. They're both related to mass in their own separate ways. We have heart rate and lifespan based off body mass. Find R times S sub M. R of M times S of M. R times S of M. There we go. Explain what R times S of M represents. I'm trying to think representation. Let's see. Heart rate times lifespan equals heart rate times lifespan. Oh, how many beats per minute. How many beats per minute you have in a lifetime, I guess. Okay, anyway. So that's what the answer is. Here's where scientific notation comes into play. I didn't realize this was a scientific notation problem. 241 times this, they're going to distribute the 241 into the 6. Notice that the 10 to the 6 is just a portion of the product. You don't distribute under multiplication. You distribute under addition and subtraction. So they just did that. They rewrote scientific notation as this. I don't know how much I need to teach on this specifically or how much I'm going to emphasize this, but when you have a decimal right here and move it 3 places over, make it 1,000 times smaller, you make up for it in the exponent here by making this 1,000 times bigger. Making this 10 to the third times bigger than it was makes it 1,000 times bigger on this side, and we're rewriting scientific notation that way. Sorry, scratchy nose. The other portion of this that, I don't know if you noticed this, but we have M's, both right here and right here, that are multiplying ultimately as a whole as well, which means the exponents add. Negative 0.25 plus 2 is negative 0.05. Sure, the exponent's negative. You could turn it positive by dividing by it. It's up to you, but this is still a scientific notation version of that. So multiplying heart rate by lifespan gives a total number of heartbeats over the lifetime of a white rhino with body mass M. Good old interpretation. All right, a pretty quick lecture portion overall. I hope the problem set is as well. Just to make sense of what we're doing, we should have some drill and kill to begin with. But first, let's start with the vocabulary and core concept check. Let f and g be any two functions. Describe how you can use f, g, and the 4 basic operations to create new functions. Well, you can add, subtract, multiply, and divide them. So I don't know. I'll say that out loud, but that's the idea. You can add these two functions together. You can subtract these two functions together. You can multiply these two functions together. And you can divide these two functions together. Now, I normally would not want to write it this way voluntarily. Okay, I would just do that. But that's the way you can create new functions. You can add them, subtract, multiply, and divide. Number 2, what x values are not included in the domain of the quotient of two functions? You're not allowed an x value that would get you to divide by 0 in your denominator. So no x values, hyphenated. No x values are allowed such that the denominator becomes 0. This is because you cannot divide by 0. Okay? Now, remember, that's of the original setup. If you simplify something and there's no more denominator, it's not that there's no more denominator. You got a rewrite of it, but you still can't divide by 0. So you have to look at that as a whole. All right, guys, we're going to go into the actual problem set itself. Numbers 3 through, what was it again? 27. 3 through 27. Hopefully these will go pretty quickly, but hopefully you learn it as well along the way. Without further ado, I'm going to go ahead and get started. Okay. Get my pen. For 3 through 6, find f plus g of x and f minus g of x and state the domain of each. Then you evaluate f plus g and f minus g for the given value of x. So on number 3, we have an f of x of negative 5 times the 4th root of x. G of x equals 19 times the 4th root of x. And then x equals 16 will be the ultimate substitution after we do both of these things. So let's start. I'll just do these in blue, I suppose. So whenever you see f plus g of x, then you hit undo. F plus g of x, that's the same thing once again as f of x plus g of x. So it's a straight up substitution. We have negative 5 times the 4th root of x plus 19 times the 4th root of x. These are like terms, if you will. So when you add those, that's 14 times the 4th root of x. This is f plus g of x. Now they're going to ask you to do f plus g of 16. So I'm going to do that before the subtraction. F plus g of 16 equals, and I know I have to do domain still. I will try to remember to do it beforehand next time. 14 times the fourth root of 16, that's 14 times 2, which is 28. Now, as far as this domain for this function goes, you cannot take even roots of negative numbers, only positive. So x is greater than or equal to 0 for that domain. We can assume the domain's going to be the same for f minus g of x as well. Doesn't seem to be a real change on that one. So f minus g of x, what you can do here is f of x minus g of x, which is going to be negative 5 times fourth root of x minus 19 times the fourth root of x. Negative 5 minus 19 is negative 24, so negative 24 times the fourth root of x is going to be this simplified version of the subtraction of those two. The domain is still x is greater than or equal to 0 because you can only take, you can't take even roots of negative numbers, only positive and 0. So let's take f minus g of 16, and that's going to be negative 24 times the fourth root of 16, which is negative 24 times 2, which is negative 48. Now, that was just one problem, right? These are going to, it might take some time. We have to copy down the problems. We have to do a little bit of work here and there. That was pretty small work, too. So, looks like it still just might take a while just because the problems have a little bit to do each. F of x equals cube root of 2x. G of x equals negative 11 times the cube root of 2x. And we're going to be substituting negative 4 for x. Now, f plus g of x, if you saw number 3, that does mean f of x times g of x. So we're going to be doing cube root of 2x plus negative 11 times cube root of 2x. So it is still addition, right? It becomes a subtraction ultimately. Now, I'm going to do some simplification anyway. I'm going to write a 1 in front of here to remind you of the coefficient that's there as I do the minus 11. These are like terms, however, and they will combine. That becomes negative 10 times the cube root of 2x, like that. Now, for the domain here, the inside must be, oh, sorry, it's in all real numbers. It's a cube root. Domain is all real numbers for this one. No restrictions on x inside there. Cube roots, we are good. We're going to be taking f plus g of negative 4, which means we get to do negative 10 times the cube root of 2 times negative 4, which is negative 10 times the cube root of negative 8. Cube root of negative 8 is negative 2. So we get to do negative 10 times negative 2, which is 20. F plus g of negative 4 equals 20. I did green last time. Let's use green for f minus g of x, where we have cube root of 2x minus 11, minus negative, was it negative 11? Minus negative 11 times the cube root of 2x. Now this time it'll become addition. Remember, there's a 1 here. 1 times cube root of 2x plus 11 times cube root of 2x. 1 plus 11 equals 12, so you get 12 times the cube root of 2x. Still all real number domain for that problem. Now let's do f minus g of negative 4, where we substitute negative 4 in there. Remember, that's still going to be the same negative 8 that we had. 12 times just cube root of negative 8 is 12 times negative 2, so negative 24. I'll speed up on some of those after we do one and then the other. I think it just makes sense to do that. Okay. As long as you saw what I did the first time to get there, it's still the same inner function for that. That's not going to be the same for each problem. These were just radicals that they had that. Like these are polynomials on the next two. Number 5, and I don't know. I'll write it exactly as it's written to begin with, but it's not in standard form. F of x equals 6x minus 4x squared minus 7x cubed, but the leading term's negative. G of x equals 9x squared minus 5x, and x equals negative 1. That's our substitution. Let's start with f plus g of x. I want to write f of x. And it's fine to do that, right? F plus g of x is f of x plus g of x, so we're going to be doing this plus this. And listen, I don't need parentheses for something where it's just addition, right? It's just going to straight up add these two. Now, I want standard form. So I'm going to start with my cubic term, negative 7x cubed, which doesn't combine. Negative 4x squared plus 9x squared is positive 5x squared. And 6x minus 5x is 1x. So there is your function here. There's no restriction in our domain for polynomials. We're going to have all real numbers. So let's get f plus g of negative 1. And this will be negative 7 times negative 1 cubed plus 5 times negative 1 squared plus negative 1. Negative 1 cubed is negative 1 times negative 7 is positive 7. This will be plus 5 and minus 1, which is 11. Let's do f minus g of x. This time parentheses is best to use for this second guy. Now f of x is still 6x minus 4x squared minus 7x cubed. The lecture portion did this as well. Subtract the quantity 9x squared minus 5x. As a rewrite after distribution, the signs inside the parentheses change when you write them without parentheses. So, in change in sign, it's minus 9x squared plus 5x. Combine like terms, 7x cubed is still negative. That didn't change, but these will. This becomes negative 13x squared, and this is plus 11x. Domain is still all real numbers for this. You will likely, for addition and subtraction, get the same domain for each, unless something is completely canceling with regard to x's. It should probably be the same. It's multiplication and division. I think you're going to see some differences on those. Anyway, and these are just addition and subtraction. So let's do f minus g of negative 1. Same substitution. This is still a 7, and this time it's minus 13. Negative 1 squared is positive 1. Subtract the 13, and we do subtract 11 from here. Okay? And that is something. Negative 17. Sorry if that's wrong. I'm going to go back and look, but sorry if I said it wrong to begin with. I think so. Negative 17. All right, one more in this set before it looks like we'll do multiplication and division, but one more set of addition and subtraction. This is with another set of polynomials. So number 6, we have f of x equals 11x plus 2x squared. And I wanted to remind you that, we're in a chapter involving radicals and rational exponents. Well, a couple of these questions aren't really about radicals and rational exponents. I think they fronted with them to say, hey, don't forget where you are chapter-wise. And even though polynomials are probably easier to deal with and where you probably do more function operation, I know why they're doing it here based on the final section being on inverses. So let's start with f plus g of x. We're going to get f of x plus g of x. Now, the only reason I might put the negative here is because that's already negative to start with. What's that called? Shot myself in the foot by putting the plus there to begin with. But listen, signs don't change. Adding a negative is subtraction. Adding a positive is addition. 2x squared minus 3x squared is negative 1x squared. Let's lead with that. 11x minus 7x is 4x, and there is a plus 4 on the back end. There's f plus g of x. Let's do f plus g of 2. Oh, domain, all real numbers. Poorly written. F plus g of 2. Opposite of 2 squared plus 4 times 2 plus 4. That gives you negative 4 plus 8, which is 4, plus 4, which is 8. Remember, the negative is on the outside of that for order of operations. Let's see how that changes for f minus g of x. So this is going to be 11x plus 2x squared. Now we're going to subtract these, which changes signs. Not from the front ones. F of x is still the same. Minus the g of x is plus 7x plus 3x squared minus 4. 2x squared plus 3x squared is 5x squared, so that changed dramatically. 11x plus 7x is 18x. That changed dramatically. And negative 4 changed somewhat. Domain is still all real numbers. All polynomials, all real number domains. Cool. Not all real number range. But they didn't ask. That part doesn't matter. F minus g of, was it 2? Yeah, 2. So we got 5 times 2 squared plus 18 times 2 minus 4, which is 5 times 4, 20, plus 36 is 56, minus 4 is 52. 5, 2. Okay. All right, that was only the first 4 problems, so okay, maybe there's a little bit of duration to be had. It was a shorter lecture, though, which kind of cuts it in time in a positive way. In exercises 7 through 12, 6 questions, find f times g of x and f divided by g of x and state the domain of each. This is where you're going to have different changes in domain. We have a little more work to do on these ones. Then evaluate f times g and f divided by g for the given value of x. So no change, only now it's multiplication instead of division. We have smaller numbers, though. It's not big polynomials. We actually hit a few more things with rational exponents and radical functions. So we're not doing this big expanding as like a, a cubic or quartic or anything like that in binomials. Maybe that saves us a little bit of time for sure. All right, let's start with, I'll do this in blue again. We're going to do f times g of x. As a reminder, this does mean f of x times g of x. So we're going to be taking 2x cubed and multiplying cube root of x. Now, I'm fine with that answer, right? I'm good with 2x cubed times cube root of x just like that. The 3's look a little weird being close together. That's fine for me. When we saw the lecture version, though, they wrote it as a rational exponent, and I'm not really sure why. It's not the big thing to me to do. This is 2x cubed times x to the 1/3 power, which means you get to keep the base from those x's and add the exponents. 3 plus 1/3, which is 9/3 plus 1/3, or 10/3. 2x to the 10/3 power. If you prefer that, more power to you. I no pun intended, that's an exponent. But I'm really bigger with that, especially when it comes to substitution, but also because that's simplified. I mean, that's a version of simplification that we're totally good with. Now, f times g, domain. Your domain here is all real numbers, and this is, once again, where when I look at the cube root thing, I can tell myself that works out. You really have to cater toward the original thing, though, as well, which is what it was. Domain's all real numbers, you can take cube roots of negatives. For example, let's substitute negative 27. Let's do f times g of negative 27, and honestly, guys, I'm going to, the calculator, I'm going to use the calculator no matter what I do. 2 times negative 27 to the, fine, let's do 10/3. I'm going to use the calculator anyway. This is a pretty big number. So if I go over here, 2 times 27. If I use parentheses the way, negative 27. If I use parentheses the way that this thing had it, and additional parentheses here, then it should do order of operations just fine, and this should be an integer. Positive 118,098. Should it be positive? Yeah, we got a negative times a negative, right? That's how that will end up because they're cubics and cube roots. Let's now do f divided by g of x. Once again, as a reminder, that is f of x over g of x. I got scratchy nose syndrome, guys. Which is going to be 2x cubed over cube root of x. Now, this one does need to be simplified. Whether or not you can argue certain things, you can't have an irrational denominator. Whether you want to choose to rationalize or go another format's up to you. I'd prefer doing exactly what the book probably would do. Turn this into its exponent, and now subtract these exponents. This becomes 2 times x to the 3 minus 1/3 power. 3 minus 1/3 is 9/3 minus 1/3, which is 8/3. So 2x to the 8/3 power. So this is an answer. There are other versions. Look, if you want to do a rational denominator stuff, in this case, you totally can as well. You can also do 2x. Let's see, 3 goes into 8 twice, and there's a remainder of 2 inside of there. So here's another answer. I can see where some people are like, that looks busier, that looks weirder. But in terms of computing things, I'd prefer that one more personally. Personally, I'd want to do that. Now, domain. Domain's tricky on this one for the division. When it comes to this domain part of cube roots, we're all good. We can take cube root of any number. But this inside of here is your denominator. You cannot have a 0 denominator. So with respect to our domain, x is not allowed to be 0. Whatever's inside the denominator, not inside the radical, the cube root of x isn't allowed to be 0. If you cube both sides, x isn't allowed to be 0. X can be any other number, positive, negative. It can be negative 27. That's what we're going to substitute. But it can't be 0, otherwise you divide by 0. That doesn't show up here or here. That doesn't show up in the simplified version. It shows up in your original. When we simplify needs to keep that domain in mind. All right, let's do f over g of negative 27. And again, I think when it comes to just calculator basis, I guess it makes more sense to substitute it in the one with the radical. So 2 times negative 27 to the 8/3. And I expect a positive number out of this one as well because of raising to the even number there. So I'm just going to type it in. And I'm getting this time 13,122. Okay, that's just number 7. So, okay, this might take a while. That was just one question. And I'm not really doing things slowly. I have a little bit of explanation, but I'm doing things as they are, right? F of x equals x to the 4th, number 8. G of x equals 3 times the square root of x. And x equals 4 will be our ultimate substitution. Let's do the multiplication. F times g of x. That'll be x to the 4th times 3 times the square root of x, which is 3x to the 4th times square root of x. That looks glorious. If you want a bookie version of it, that's 3x to the 9/2, I suppose, because this is x to the 1/2. 4 plus 1/2 is 4.5, or 9/2. So here's a version. Now, as far as domain, you have to keep in mind there is a square root. There is, there was, there will be. So as far as domain goes here, we need to stay positive. Stay happy. So greater than, or sorry, you can be 0. Greater than or equal to 0 is allowed here. Let's do f times g of 4. I'm going to substitute in this one. I kind of want to use the noggin for this one. So this is going to be 3 times 256 times 2. 512 times 3. 1,536. I believe should be that answer. All right, let's do division. F over g of x is x to the 4th over 3 root x. Let's just talk rationalization of denominator to begin with. Let's multiply top and bottom by root x. You get x to the 4th root x all over 3. 3x, I should say. And these, I can remove an x from bottom, remove an x from top, and now you're left with x cubed times the square root of x, all divided by 3. Another version of this, you could do something like 1/3. I mean, listen, it depends on if you want to write as a fraction version like that, or all divided by. 3 plus 1/2 is 3.5 or 7/2. So you can do, excuse me, x 1/3 x to the 7/2 power. This is fine. A lot of different ways you can write it. Now, regarding domain, you still have a square root of x involved, so you have to have positives or 0. However, there was a square root of x in the denominator that you have to, that's the rationalization. There's a square root of x in the denominator you have to be careful with as well. It's not the square root of x part that matters, it's just the denominator itself. So when I write out domain stuff, and I'll just write it on the side, 3 times square root of x is not allowed to be 0, period. Doesn't matter about the square root portion, it's just the denominator can't be 0. If you divide by 3, the square root of x can't be 0, and if you square both sides, x can't be 0. So your domain, x is not allowed to be 0, it's not allowed to be negative. Your domain here is x must be greater than 0. Positive numbers only. There are 2 portions of the restriction, the square root portion and the denominator portion, and we have to adhere to both. Now we are going to be doing f over g of 4, which is again f of 4 over g of 4, and we have a simplified version of it here. 4 cubed times the square root of 4 all over 3. Being a smaller number, I think this will help out. 64 times 2 over 3. Oh, that doesn't divide evenly by 3 though, does it? So 128 over 3? I think it would just be left like that. I don't think you can do anything when it comes to that division. So I'm just leave it as 128 over 3. We'll have some fraction answers. I'm going to believe that as such a thing. So just get ready for some of those. Okay, that was number 8. Okay, let's go on to number 9. F of x equals 4x. G of x equals 9x to the 1/2 power, also means square root of x. Not the 9, just the x. And x equals 9 will be our substitution. Let's multiply. F times g of le x. 4x times 9x to the 1/2 power. Now, the 4 and the 9 can multiply. 9's not being raised to that power at all, so we can turn that into 36. X times x to the 1/2 is, you can write it as x times square root of x. This is a good one. Oh, that's a good one. You could also do it as x to the 1 plus 1/2 or 1.5 or 3/2 power. That's good as well. Which do I prefer? Probably that one. Domain can't take the square root of a negative, so we're saying just that, only positives. Okay. Now f times g of 9, let's use that first one. 36 times 9 times square root of 9, which is, oh, I don't know if there's 360, 324. 324 times 3, which is 972. I hope. Trust in oneself. F over g of x is 4x over 9x to the 1/2 power. Now, if I write my version as 9 times the square root of x, I can rationalize the denominator by multiplying top and bottom by square root of x. And now you have 4x root x all over 9x. These x's can cancel, and that will be 4/9 root x, if you want to write it like that. 4 root x over 9. 4/9 times the square root of x. Maybe that's a good version you can write. Or 4/9 x to the 1/2 power. Something like that. Square root still involved. X can't be negative, so greater than or equal to 0. But because of this denominator here that you see, you also can't be 0 for x. Square root of 0 is 0 times 9 is 0. X can't be 0 as well as less than 0. X must be greater than 0 for our domain. So there's that. Our last thing to do is substitute 9 into any of these. I like that one there. We got f over g of 9, which is 4/9 times the square root of 9, which is 4/9 times 3. 3/9 is 1/3, so you get 4/3 as your answer there. And as long as they're giving us values to input that exist within your domain, then you should always get values out. So there's nothing wrong with that. I'd say we're all good on that one as well. Okay, let's go to number 10. Number 10. Yeah, these are taking a while. I was hoping like, oh, good, it's a quick, 1 through 20. Time per problem, probably even more than graphs. F of x equals 11x cubed. Definitely more hand cramp on this one for me. G of x equals 7x to the 7/3. So if there was any doubt as to which chapter we were in, I think that this set of problems is a good reminder that we're still on radicals and rational exponents. Do they have to use these here? No. However, and if it was multiplication, they could do polynomials on day, and distribution would still take a while. However, if it was division, I will state, I think I already stated it, there is a later chapter where we are doing rational functions, and they will deal with polynomials divided by polynomials. Not right now. You could use long division, but there's more to it than just that we'll talk about in a different chapter at a different time. Anyway, so we're multiplying these two here. 11 does get to multiply with 7. You get 77. Now, x to the 3 plus 7/3. That would be 9/3 plus 7/3. Let's start with this format of it, the rational exponent version. That's x to the 16/3. So there's one version. I'll box that. If you'd like the alternative with radicals, 3 goes into 16 5 times. So we'll have x to the 5th there. And there's still a cube root. There's still a 1 remaining inside the cube root, like that. So here's another version. 77x to the 5th times the cube root of x. Now, given that this is a -8, this sniffs, I'm going to use calculator anyway, so I'll probably do it with this form. The domain is regarding your roots. It's a cube root. So we're all good on cube roots. We have an all real number domain thus far for our multiplication set. Division will be a different story for dividing by 0. But f times g of -8, let's do 77 times -8 to the 16/3 power. And here's the thing, we're going to raise to an even number anyway. It looks like it's just going to end up, what do you call it? Turning positive. So let's go ahead in that one. I was going to show you, but I don't think you need to see these ones. 77 times -8 raised to the, in parentheses, 16/3 power. Okay. 5 million, yeah, needed a calculator. 5,046,272. Ayo, I learned a lot about that. What have we learned over the course of random numbers? F over g of x equals 11x cubed over 7x to the 7/3. Okay, let's see. Let's do, not rationalizing denominator, this time let's do subtraction of these. Now 11 over 7 remains as is. There's nothing we can do with that. 11/7 is just what it is. This is 9/3 still, right? 9/3 minus 7/3 is what's happening here when you divide these. And that'll be to the 2/3 power. So this is 11/7 x to the 2/3 power. There's a version of the answer and a fine one. This is also 11/7 times the cube root of x squared. Now, domain for this one is not all real numbers because, once again, you can't divide by 0. And again, when we get more into rational function talk, guys, they're going to get a lot different than just x can't equal 0, x can't equal 0. It's that the denominator can't equal 0. It just so happens that x is the substitution that'll get you 0 in the denominator for our current set of problems. But when we hit rational ones, oh, we'll get anything. X can't equal 3/4, x can't, just whatever it is. -8's our substitution this time. Let's plug it into there. 11/7 times -8 to the 2/3 power. I guess that'll probably be a fraction because the 11/7. So listen, I'm going to type in my calculator 11 times -8 to the 2/3 power. I'm not going to divide by 7 yet just because I don't think this number is going to divide by 7. Right? There's no reason why it would. These are not multiples of 7. And they don't have any prime factors with 7. So that number is 44. So ultimately, my final result looks like 44 over 7. And I was right. 44 does not divide by 7. So 44/7 is what I'll leave it as. And we're going to be happy about that. All right. Let's go to number 11. F of x equals 7x to the 3/2 power. G of x equals -14x to the 1/3 power. Ooh, different denominators. And x equals 64 as a substitution. So hopefully the numbers are small. As far as multiplication goes, f times g of x equals, we'll do 7x to the 3/2 times -14x to the 1/3. It's not really all that small. 7 times -14 is -98. And now they're both x's. We got to do 3/2 plus 1/3. For common denominator's sake, we'll multiply this by, let's use a different color. Multiply this by, because we're going to do this for the subtraction one as well, right? We'll just do a subtraction of these. So we'll just keep these in mind. 3 over 3, and this is 2 over 2. So this will be -98 to the, or times x to the 9/6 plus 2/6, which is 11/6. I have trouble saying that word. Say sixths. Sixths. -98 times x to the 11/6 power. If you don't want to say sixths, you can say the 6th root here. If you do, -98. 6 goes into 11 once with a remainder of 5. Here's an alternative version. This is a square root originally. I know it's multiplying by a cube root here. Remember, square root, cube root. Don't change the fact that there's that. If that helps remind you, there's still an even root here. You can still plug in negative numbers here. It'll stay negative, and then take the even root. That'll be trouble. So x still must be positive. X has to be greater than or equal to 0. Now, 64 is greater than or equal to 0, and we're about to substitute that right now. F times g of 64. We got our function. None of this is going to look good, so let's just use this one here. -98 times x, 64, to the 11/6 power. It should be big. 11/6. Negative, was that expected? Yes. Negative 200,704. All right, f over g of x. 7x to the 3 halves divided by, I think it was negative 14x to the 1/3. Negative 14x to the 1/3. All right, let's start with the numbers. These ones will actually reduce. Negative 7 over negative 14 is negative 1/2. So I'm going to start with just writing negative 1/2. That'll remain. Now, remember, we're going to subtract these two, and we have the common denominator versions of these. Listen, we're going to subtract because it's division, right? So 3 halves is also 9/6, and 1/3 is also 2/6. So 9/6 minus 2/6, which is going to be negative 1/2 x to the 7 over 6 power. Write it more like an exponent than I did. In fact, let's do that again. And I'll give you the other version that you might want to do, which is negative 1/2. 6 goes into 7 once, and then and there's a 1 remainder, like that. Whichever one you prefer is up to you. Still can't take even roots of negative numbers, but you also can't divide by 0. So x is greater than 0. Okay, doesn't matter that it cleaned up to something here where it started before is your true division. This is just a cleaned up version that we have to still account for. I can't stop restating that. All right, f over g of, I think the number was 64. Confirmed. Yep. We're going to do negative 1/2 times 64 to the 7 over 6 power. Listen, the number's not going to be much more than, if this is close to 64 to the first power, so it'll be close to 64. It'll be bigger. And we've got to take half of that number and make it negative. So half of 64 is 32. So it'll be more than negative 32, maybe negative 40, maybe negative 50. Maybe it's not a whole number. I don't actually know. Let's take a look. Negative 1/2 times 64. I'm just saying in terms of answer anticipation, if you screw something up in your calculation, know what to anticipate. This time I can get a feel. Oh, negative 64. There's probably a reason why I should have known that. Oh, yeah, 6 root of 64 is 2. Oh, yeah, I could have done that here. Half of 2 is negative 30, so negative 32 times 2 is negative 64. See, I would have done better with this one. There it is. I would have done better with that one. Number 12. Number 12, we have f of x equals 4 times x to the 5/4 power. G of x equals 2 times x to the 1/2 power. And x equals less 16. So f times g of x. Are they going to try and trick us? I think it's just more like number 11. 4x to the 5/4 times 2x to the 1/2. We can do 4 times 2 and get our 8. And then we got to add these two, 5/4 plus 1/2. Let's get common denominator. This just needs to multiply by 2 over 2. Okay, so it's 5/4 plus 2/4. So equals 8x to the 5/4 plus 2/4 power, which is 8x to the 7/4 power. There's an answer, or 4 goes into 7 once with a remainder, 4th root of 3. Now we're going to substitute 16 into here. I can't imagine a version that I can do very well. You know what? I can do some of these well. I just think of the cube before the 4th root. I can take the 4th root of 16. Let's try this one here. Let's try this one in our head. F times g of 16, I'm going to do 8 times 16, I guess that's kind of big, times the 4th root of 16 cubed. Remember, you can do the 4th root of 16 first. So the 4th root of 16 is 2, and 2 cubed is 8. So it's 8 times 16 times 8, or 64 times 8. 8 times 16 times 8. Or, excuse me, 64 times 16. I think it's 1,024. I think it's 1,024. Let me check as a for sure. I like to do some of these things in my head to start with, but it's at this stage that 1,024. Okay. I like to still confirm my head. Confirm my head is still intact. All right. F over g of x equals f of x over g of x, 4x to the 5/4 over 2x to the 1/2. So the 4 over 2 will become 2. The exponents will subtract here. Remember, it's 5/4 minus 2/4 now in that case. So this is going to become 2x to the 3/4 power. And that's one version to write. Or 2 times the 4th root of x cubed. And I can do that one in my head as a for sure. That's still, oh, I didn't mention domain. I'm going to get to that. I hope I did domain for all the other problems. So I'll do it for both as a whole here in just a second. F over G, I got so stoked that I could actually do a calculation there. What number was this? 64, 16? 16. F over G of 16 will be 2 times, I'm going to do this one, the 4th root of 16 cubed. And we just saw this. 4th root of 16 is 2. 2 cubed is 8. 2 times 8 is 16 back. Input 16, output 16. Not very common. I think it happened for 64 on the other one, though, so I guess common enough. All right, let's go back to our domains. Domain for this one can't take the 4th root of a negative number, so for domain here, greater than or equal to 0. Same's going to be true at the bottom, but we also can't divide by 0, so that's true for this guy here. So x must be greater than 0 as a whole for this set. X is greater than 0. So again, sorry if that doesn't feel, you know, diverse and with a lot of variety, but I guarantee you we are going to be getting some of those in the future. Maybe not this chapter, but in future chapters for domain things. Trust me, it's not just always 0 that it can't be. All right, in 13 to 16, use a graphing calculator to evaluate these ones when x equals 5. Round your answers to 2 decimal places. All right, so we're going to start with this one. We'll call this our y1. And this one we will call our y2. So it's straight to calculator. We're just going to let it do it. So we're going to figure out basically, well, I'll write them afterward. Let's go to the calculator for that. And what we recognize we do is we type in one of them for our, say, y1. This one for our y2. This might be a little quicker here. We'll find out shortly. 1/3, put that in parentheses. So our y1 and y2. Now, I don't know if there's a shorthand way to type y1 and y2 for these kinds of things. I want to try something in a second here, but let me clear these out so you get a clean slate. So we go to vars, that's variables, y variables in function, and enter y1. Now we're going to substitute for all of these 5. We're going to substitute 5. We're going to do this for addition for the first term and the second one. Actually, I don't need to do shorthand. I can just keep recalling this. We're adding these two. So this is what happens when you substitute 5 into both of these. And I'm not going to do a double check thing. I'm going to trust the calculator. But this is where they are doing f plus g of 5. They're doing f of 5 plus g of 5. Even if you didn't combine things or anything like that, plug in 5 into here. 5 to the 4th times 4 plus 24 times the cube root of 5. Okay. Now that approximation to 2 decimal places will be 2,541.04. 2541.04. That is the sum of those two there. Now we're going to do f minus g of 5. The really cool thing about the calculator here, and I'm going to try and really go faster for some of them as you learn it, is we can recall second, enter, recall this, and turn this into a subtraction. It's the same two functions and just subtract. So I think this will go pretty quickly as a whole for this. This is 2,458.96 rounded. So that's what I wrote for this guy. And let me do the last two on multiplication and division, and then I'll just write them down afterwards. So again, there's some speed on that. So multiplication, this times that, and then division, this divided by that. That's what happens when you substitute 5 for those ones. So I'm going to do f times g of 5 to be about 102,598.56 when rounded. So it's just a lot of entering the calculator. And f over g of 5 to be about 60.92. 60.92. I'll try and clean up my handwriting for those ones. All right, there's number 13. Yeah, there's not much to say on these things. We are going to substitute 5, and we can recall all of those things for these other ones. So the only difference on number 14 and all that, as I write down the problem, is I will simply change the y1 and y2. I get to recall those previous entries, which is really nice. So this should go pretty quickly on this set. It's 5/3. G of x. What looms behind this problem set for the last 11 problems? I don't know. Probably some error correction, but word problems obviously are part of it. I mean, there are things that you can do. I can see in division a lot of things that I can get for this answer. I believe I already know the division answer as something. Anyway, I'm seeing the numbers because 7 over 49 is 1/7. And then he gets multiplied by 5. I think it's going to be 5/7. Sorry, I'm just imagining the division one. I think the answer is going as a decimal. I don't know if 5 cents is a decimal. Around 0.71, I think. I'm going to be happy if I figure out that that's it. Anyway, let's add, because these can't combine as like terms or anything like that. So we're going to input these. So 7x to the 5/3 and 49x to the 2/3. All right, so here's our recall status, right? I can just go back. I mean, let's do this. Let's clear these out first and get to addition. So here's addition. You have to enter a few times to go back, though. Subtraction. Oh, let's just recall any single one. Multiplication. Sorry about that. Multiplication and division. All right, is this going to be the 0.71-ish number that I thought? I got it. All right. All right, so I'm going to write down those four. This top one's addition. Here's addition, subtraction, multiplication, and division, okay? So what I probably should do, I still have 2 more problems to do this, so I think it's worth doing it now, is let's just write like f, and I'm gonna try to make the handwriting look really good. F plus g of 5 about equals, and then we'll do f minus g of 5. Like I said, I'm going to try and streamline everything significantly more. I don't really have much to say on these ones, so I think it's better that we just mosey on forward. I should just not do these problems, right? You don't need me for these. But little shortcuts and stuff like that. Okay. I can copy and paste that each time now, which is nice. And then I just got to write my numbers. So the numbers were what they were. I'm going to say them. I'm going to put them right here. So 245.62. Negative 40.94. 14,663.04 and 0.71. Oh, happy day. Okay. Copy that and get it ready for the next set. Number 15. F of x. F of x equals negative 2x to the 1/3. G of x equals 5x to the 1/2. Okay, you know what I want to do? I want to do all of those. Oh, that's much better for me. You got to write them if you got this problem to do. I don't think I have to do quite as many problems as I do. All right, we're going to do, let's clear these out. Oh, we have to retype the equations, huh? Otherwise we get the same numbers and go, hey, every function's the same. Negative 2x to the 1/3. I should really just do cube root of x. Come on now. They're really pushing this rational stuff, and it's irrelevant to me. 5x to the 1, it's irrelevant just because we're typing them in a calculator. 5x to the 1/2, or square root of. Okay, so let's do addition, subtraction, and I don't know what to expect for these answers, but here they are. Multiplication, and division. Okay, I'm going to write down these numbers. Addition, subtraction, multiplication, division. Here we go. So we're going to get about 7.76. Yikes. Negative 14.60. Negative 38.24. And I just have to trust it's right. I mean, I hope I typed it incorrectly. And negative 0.31. Okay. One more on number 16. You can see how they're getting a little bit faster. I think I can't really change the speed now. The speed is what it is. So f of x equals 4x to the 1/2. You know what helps me, though, is it's a little less writing for me, especially when I get to copy paste. I get some time to calculate. Helps my little hand cramp thing that I sometimes get when I have to write all that stuff really quickly. That tends to kind of hurt. All right, so this is 4x to the 1/2. You can put 0.5 if you want, or square root, right? And 6x to the 3/4. And again, with these problems, like I don't feel like I'm like learning anything new with each time I do this. It's just I'm just typing in whatever I get. I'm trusting it, and it is what it is. So try it a couple times, feel good on it, and move forward. There's no like, what did you notice about these? The only one that I actually did was that 0.71 value, where I noticed that the things would become what they were. Anyway, so for this set, I never pasted that other thing over. With this set, I just got those numbers. If you want to see them one more time, here they are. Okay. Plus, minus, times, divided by. Let's go back. Okay. 29.01. Negative, it was close. It was negative 11.11, but it rounds up to 1.2. 179.44. I like my numbers to look cool. You know what I mean? And 0.45 when rounded. All right. Those are probably the quick ones. Let's move forward to the next set. Here's our error analysis. In exercises 17 and 18, describe and correct the error in stating the domain. So in 17, they say f of x equals x to the 1/2, g of x equals x to 3/2. Domain is all real numbers for multiplication. Now, I can understand why they might say that. Here's the idea when you multiply them, right? X to the 1/2 times x to the 3/2. I know they didn't simplify it, but that would be 1/2 plus 3/2, which is 4/2, which is 2, x squared. And you get, for f times g of x, you get that there. You're saying, hey, there's no problem with this. But there was a problem to begin with. This is square root of x. This is square root of x cubed. These can't have negative numbers inside. It doesn't matter what they become when simplified. This is equivalent to it for all x's that exist in the initial domain for these x's. So it's not all real numbers. The domain is positive and 0, right? The domain isn't all real numbers, despite the simplified version of the problem not appearing to have domain restrictions. You must adhere to the original problem's domain restrictions. So, with that said, domain is x is greater than or equal to 0. Domain is x is greater than or equal to 0. Okay, number 18. Once again, about domain. There are a lot of other things you can do for error corrections on these ones, but it seems like they're going to stick to domain. Domain is all real numbers except x equals 2. Okay, so at least with this one here, we have some more things that we can talk about. So this is a f over g. So I'm going to start by writing some things here. F over g equals x cubed, just so we can identify this, x squared minus 4. At least this is an example. And we're going to do more things with these later, especially when they're bigger polynomials or quadratics. We're going to do more things with these in a different chapter. But this time for this domain, this can't be 0, right? X squared minus 4 can't be 0. And they're right. X cannot be 2. However, and I guess we're correcting it before we're answering it, but the correction is telling you what else is there. It also can't be negative 2, plus or minus 2. That's our domain for this one. Negative 2 squared minus 4 is still 0. There's no problem with x being 0. 0 squared minus 4 is negative 4. You can divide by negative 4, and you can divide from 0. There's no problem with that. There are no cube roots or square root, of negatives, anything. There's no issues with that. It's just that they're missing a value in your domain. They're missing a value, not in their domain, in their domain restrictions. And their domain restrictions. X also cannot equal negative 2. Otherwise, you would still be dividing by 0. So that's more of what you're going to be doing in the future on these. It's not just, can't be 0, can't be 0. The denominator can't be 0, but x, it all depends on what's down there. If it's a monomial, yeah, maybe not 0. Okay, numbers 19 through 20. 19 and 20 are modeling with mathematics. 19 through 27 are what remain. 27? Yeah, 27. Number 19. From 1990 to 2010, the numbers in millions of female F and male M employees from the ages of 16 and 19 in the United States can be modeled by this and that, where T is the number of years since 1990. Okay, so let's copy those two down. We have F of T. This is number of, employees. Negative 0.007 t squared plus. I wonder if this stuff's accurate, right? We talk about the scientific ones that are accurate. I wonder if they do studies on these ones here. Like, I wish that there was a little like footnote and it said this information came from the, you know, whatever you call it, the census, this data. This is in millions? What is this? In millions. All right, part A. Find, sorry, not find. They can say find. I'm just going to write it straight up. F plus m of t. Now, as a reminder, this is f of t plus m of t. So that'll equal, I don't know. Can we go straight into it? We have, it's this plus that. Keep the signs the same. Just make sure you combine like terms. So I have the t cubed for the male one. Female one doesn't have that. So 0.0001 t cubed. I don't want to mess up the zeros. Now I have negative 0.007 minus 0.009, which is negative 0.016, like 16. And then 0.10t plus 0.11t should be plus 0.21t. And then the two 3.7s is 7.4. I think that's all I got to write for that. That's part A. Part B, explain what f plus m of t represents. Yeah, I guess we're not substituting any numbers in for t, which is, oh well. I wanted to do some more things about the 1990 to 2010 and what does this mean for this year. But this just means the total number of employees for both genders. F plus m of t represents the total number of employees, 16 to 19, of both genders, of the male and female genders, for any year since 1990, t since 1990. I'm trying to kind of complete what they say, but it's just the total. You add them both together and that's what you get. If it did f minus m, it's how many more females there are than males for any year and things like that. But they're not expanding on that one. They might for a different question. No, number 20 looks more of the same. Well, I kind of just revealed what this one would have to do with. Maybe it's not males and females, but this time they're subtracting. From 2005 to 2009, the numbers of cruise ship departures in thousands from around the world, W, and Florida, F, can be modeled by the equations here. So W, okay, notice we're going to do a subtraction of these. Let's see if I can kind of line these up to start with, knowing that, so I don't have to write any additional stuff. Looks like a repeated 3, my friends, plus 17.43 t squared. I hope I can fit this. That's a lot of departures. This is just the initial in the year 2005, and that's in thousands. So this is like 11 million, 11.5 million. I guess it's just departures. All right, this is also a cubic. So 12.5 t cubed minus 16.29 t squared. And this is just Florida. Oh yeah, Florida has a lot as well. All right, so part A, W minus f of t. Now this is going to be W of t minus f of t. That means this minus that. So I'm going to use the calculator for some of them to not make a mistake. I believe it's negative 18.3, not repeating, but actually I should know that one. That should be negative 18.3333. Let's write that a little better. This looks messy, dude. If I look back, I got to be critical of myself. That doesn't look good. It's probably still not going to look much better, but 18.3333. I just hope the answer's right. This one here, minus a negative will be plus. So this will be 77.72. Just keep in mind, make sure you know what I'm doing on these ones here. Plus this minus that. I think that's one I should try in my head. 372.5. Now, I've made mistakes before. This could be, no, yeah, 372.5. And I actually ran out of room on this one. This one I'll just let the calculator do it. 11496 minus 4881. All right, 6,615. 0.6615. Remember, that's in thousands as a whole, but that's part A. Part B, what does this mean here? This is how many more ships have departed in the world at any year T. What's T? Since 2005, at any year since 2005, things like that. So because it's a subtraction, it's the difference. It's the W minus F of T represents the difference. I could say that. How many more cruise ship departures there have been in thousands around the world versus Florida at any given year T since 2005. I guess that's how I say it, or at any number of years T since 2005, something like that, but that's just what I want to work off on that one. So, same idea, working it, hope you're feeling it as well. Now, I just hope that subtraction's good, right? I did a lot of it in my head, and my head can be a little screwy, but 0.72, negative 0.3, etc. I think it's good. Okay, so let's go to number 21, making an argument. Let's see how the friend's doing. Hasn't been good lately. Your friend claims that the addition of functions and the multiplication of functions are commutative. Is your friend correct? Explain your reasoning. Your friend might be right this time. Addition is commutative, multiplication is commutative. I can't see any reason why not. Now, commutative just means that you're reordering the way that you write it and you're good. I'm going to say my friend is correct. My friend for once is correct. My friend is correct. Addition and multiplication are commutative. Even under function operations. So what they're saying there is that, like, for example, f plus g of x is the same thing as g plus f of x. And f times g of x is the same thing as g times f of x. And remember, I hate writing it this way, but doing f of x plus g of x should be the same thing as g of x plus f of x. For subtraction and division, no. Right? It's the same thing. What if f of x is 5 and g of x is 3? 5 minus 3 isn't the same thing as 3 minus 5, but 5 plus 3 is the same thing as 3 plus 5. So, friend is correct again. It's been a minute. Glad to have you back, buddy. Can't wait to see you wrong again. I don't want to keep poking fun if you can get a streak of being right. Number 22, how do you see it? The graphs of the functions are shown. I've got a parabola and a line. Which graph represents the function f plus g, the function f minus g? Explain your reasoning. So f is the parabola, g is the line here. What you got to do, and you can probably understand which one is which just by, oh, this one's smaller, this one's bigger. What you got to do is understand what the y's are for any given x. What the y's are for any given x. And let's put it this way. I got an x value here, at x, I got a y value here of 4. This y value is probably negative 1. What happens when you add 4 with negative 1? Well, you get 3. Which one has 3? Oh, excuse me. And negative 1's the f. So negative, even though addition is commutative. What's negative 1 plus 4? It's 3. Which one is at 3 when y equals 0? It's that one. Now, what if I did negative 1 minus 4? Because it's not the same thing as 4 minus negative 1. But negative 1 minus 4, that would be negative 5. Which one is that? That looks to be right here. So you can see which one looks like addition and subtraction just on that one. Or let's say these crossed, I can't guarantee it, probably not. But let's say that these crossed at y equals 2. Right, just at that x value. Now 2 plus 2 would give you 4, but 2 minus 2 would give you 0. Whatever the thing is, you're doubling up on one and then you're canceling them out on the other. So the f plus g is going to be b, and f minus g is going to be a. The idea is take the y values for those x's and add them together or subtract them. Sampling some of the points, sampling some of the y values for x, for certain x's, I have obtained g value, matching sums and differences. I mean, the real one we should look at here is that also b is higher up and a is lower down. And when you consider what these two functions represent, they have a lot of positive y values going on. So when you add positive positive numbers together, they're going to get bigger as a result instead of subtracting and becoming smaller. So that's just kind of what I have with that. I think that's how I can make most sense of it. But that substitution is there. Okay, number 23. The table shows the outputs of the two functions f and g. Use the table to evaluate f plus g of 3, f minus g of 1, f times g of 2, and f divided by g of 0. I think it's good for me to go back and remind you of what the heck these things mean as a whole. We're going to copy that table down. Actually, no, the table's going to stay there, if that's okay. So when we do f plus g of 3, I want to remind you that that is f of 3 plus g of 3. And I want to remind you what function notation means. Substitute x, get out a y. So they're saying, what is the y when x is 3 for both things? When x is 3, this y is 10, and this y is negative 31. So when we're doing this, we're going to be doing 10 plus negative 31, or 10 minus 31, which is negative 21. That's f plus g of 3. It's a substitution of those two. And remember, we're using the same input. For all these, we're using the same input, but a different operation. It's not f of 3 plus g of 1. Right? We're doing the same one for both. So there's f plus g of 3. Let's do f minus g of 1, which is f of 1 minus g of 1. F of 1 looks like it's negative 4. G of 1 is negative 3. We are subtracting negative 3 from negative 4, so it's negative 4 plus 3, which is negative 1. Okay? F times g of 2 equals f of 2 times g of 2. F of 2 is 0. Well, the result's going to be 0. So 0 times negative 13, which is 0. Period. And f divided by g of 0, that doesn't mean we're dividing by 0. We're substituting 0 for x and getting y values. Maybe it is. But this is f of 0 over g of 0. F of 0 is negative 2. G of 0 is negative 1. Negative 2 over negative 1 is 2. Now, if we could figure out what these functions were, f of x and g of x, we could have actually done the operations, simplified them, and plugged them in, but that would have taken significantly longer. But I'm just saying that there are a lot of ways to do these depending on what you want to do. Number 24, thought-provoking. Doesn't that mean open-ended to us, I think? Is it possible to write two functions whose sum contains radicals but whose product does not justify your answers? Sure, I think they brought one up. I think it was the, not the your friend argument. Which one? This one. This number 17. Absolutely. So let's, the x to the 1/2 and stuff, right? I'll use them as square roots because they said radicals. But yeah. Yeah. Weird looking y. So yeah, totally. Yeah, totally. All right, here we go. Let's say, let f of x equal 3 times square root of 2x, and let g of x equal negative 5 times square root of 2x, whose sum contains radicals, whose product does not. So here we go. F plus g of x. Remember, that's f of x plus g of x. That's 3, 2x, plus negative is minus, so minus 5, 2x, and that's negative 2. I keep saying of 2x, times the square root of 2x. So there's radical. Now let's multiply them. F times g of x is going to be 3 root 2x times 5 root 2x. Root 2x times 2x is 2x, and 3 times 5 is 15, and that equals 30x. Now, when it comes to domains, which we're not talking about, both of them are x is greater than or equal to 0. It doesn't matter that this thing cleaned up, but yeah, totally. Rock on, dude. All right, number 25, mathematical connections. A triangle is inscribed in a square. They didn't say what type of triangle, they just said it's inscribed. As shown, write and simplify a function r in terms of x that represents the area of the shaded region. Okay, this is one to copy and paste so I can talk manipulation here. Now, it doesn't matter how the triangle legit fits inside there as long as it's inscribed, meaning it doesn't matter if it goes straight up the middle or more off to the side like that. Heck, it could go all the way to the edge. Maybe the edge helps you understand it best. The shaded region will still be the opposite of whatever it is, and I think I just represented the shaded region pretty well that way. If you notice, because I'm going to predict it here, if you notice, your triangle could just be this half of what this is. Let me kind of thicken this out, right? This could be the triangle, and then this could be the shaded region right here. So it's literally going to be half the area of the square. My guess is the area is going to be 1/2 x squared. But let's come up with a different version on how to come up with that other than just being half of the square, which it is, right? But, wait, why is this hard? Or based off function operations and stuff? I'm actually not sure. Anyway, so let's come up with the area of the triangle first. Area of the triangle is 1/2 base times height. The height is still x. So that itself is 1/2 x squared. Oh, this is why. Because r is taking your area, the area of the square, excuse me. The area of the square is x times x, which is x squared. So r equals the area of the square minus area of the triangle. I guess if you wanted to do something specific, you could call the area, like, let the area be f of x. Let the triangle area be g of x. And f minus g of x is x squared minus 1/2 x squared, which is 1/2 x squared. Normally I don't use blue for this writing, but there it is. So r is 1/2 x squared. That's what it is. Okay, number 26, rewriting a formula. For a mammal that weighs W grams, the volume B in milliliters of air breathed in and the volume D in milliliters of dead space, the portion of the lungs not filled with air, can be modeled by this. Man, there's a lot to have written here. B of W equals 0.07 W. D of W equals... I'm going to pretend like I understood what I read to begin with. I'll just keep reading on. The breathing rate R in breaths per minute of a mammal that weighs W grams can be modeled by this. R of W equals 1. There's B of W, D of W. 0.734. A lot of these are just substitution kinds of problems. They look ambitious, but then ultimately they're not. I'm going to first write B of W and D of W. B of W minus D of W. Okay, simplify R of W and calculate the breathing rate for body weights of 6.5 grams, 300 grams, and 70,000 grams. So we're going to do R of W equals, we got 1.1 W, 0.734 divided by 0.007 minus W. 0.002 W. Wasn't there supposed to be scientific notation in problem? Maybe this one's scientific notation. But I was going to say, weren't there supposed to be problems with scientific notation? Based on the lecture and based off the target word thing. Maybe this is considered a scientific notation question. We'll see. Probably, actually. There are things I can do with this. I'm going to kind of try and explore it with you guys. We don't have to write in scientific notation, though. That reduces to that. Now, we can do 1.1 over 0.005. 0.005 is 1 over maybe 2,000 or 20,000 or something like that. I don't know. But let's just go to the calculator for a little bit. I'm going to do 1.1, because this should be like a clean number. 0.005. That's 220. So this becomes 220. And then W, remember there's a W on the bottom, that's W to the first. So this is 0.734 minus 1. Is that 0.266? Negative 0.266? 0.734 minus 1 is negative 0.266. So if we were to do scientific notation, and I don't know if we're supposed to here. Well, a couple things. I can rewrite this as 220 over W to the 0.266 power. That's kind of a version. The denominator's not rationalized that way, though. I don't know. You know what? I'm going to leave it like this negative one. Because, I don't know if this is a scientific notation question. Maybe the next one is. What's the next problem say? Next one doesn't look like scientific notation. So let's just kind of do a scientific notation version. Did they say to do that? They didn't. So I could rewrite this as 2.2 times 10 to the second power times, I forget if that's where they put it, like that. I mean, I'm not going to work it that way. I'm just going to leave it like that. This is also fine. 10 to the second power is 100. I move that 2 decimal places over. There's one or the other. They both kind of work. It just rang a bell to me that we never use scientific notation. Anyway, that would be the kind of part A. Breathing rate for body weights of 6.5, 370,000 grams. Now let's make sure that everything we did here was right. So W's in grams, R's in breaths per minute, B and D are in milliliters, and they use W. So I think it's literally just a substitution here. We're going to be doing R of 6.5. Now I'm going to use the calculator for all of these. R of 300 and R of 70,000. Probably approximately equal to on all three of them, and I don't know what kinds of answers I expect. At this point, it's more just calculator usage. So I'm actually going to go to the equation portion and do it this way. We'll even use that function that we used before. So I'll do 220 x to the negative 0.266 power. And let's use y sub 1 of 6.5. We could use the table feature as well. Y sub 1 of 300. And, less. And y sub 1 of 70,000. Less. Okay, so what are they talking about? Breathing rate. So if you weigh more, you breathe less, right? You can think of like a big, like a whale or something like that. I don't know. All right, so 6.5, we're going to get about 133.7 breaths per minute. I don't want to put BPM because that's beats per minute. And then next one is 48.3. Probably shouldn't use the decimal. Probably just 48, 134. Right, decimal is kind of weird, but that's all right. 11.3 breaths per minute. It's kind of in the middle of the numbers, so I kind of feel like I'd want to put those. Okay. So yeah, guys, with those ones, it's generally just a substitution of what we're doing there. I think they're fine to do, and then, yeah, we're good. I don't really know how I want to write the equation, though. That's the part where I'm thinking, like, do we simplify it? Do we leave it rationalized? I don't really know. I wanted to use scientific notation, so I kind of gave you a version. All right, the last question is number 27 on problem solving. Trying to fit the whole question on one shot. There we go. A mathematician at a lake throws a tennis ball from point A along the water's edge to point B in the water. Is this a top-down view, or is that water? How would it curve? His dog Elvis first runs along the beach from point A to point D and then swims to fetch the ball at point B. Okay. I don't know how the curve works for the throw, but along the water's edge, point B in the water. I guess the curve's just showing, oh, that's the throw. Okay, that's okay. Okay. Elvis runs at a speed of about 6.4 meters per second. Is Elvis the dog? Yeah. 27. I think I need to copy paste this picture here. All right, 6.4 meters per second is le Elvis. Write a function r in terms of x that represents the time he spends running from point A to D. Elvis swims at a speed of about 0.9 meters per second. Write a function s in terms of x that represents the time he spends swimming from point D to point B. Okay, first of all, because I gotta think through this problem. I gotta talk out loud. From A to D, I want to make sure that you know A to D is the distance of 20 minus x. I don't know what the x has to do with the problem yet, but A to D is just this distance right here. Take the 20, subtract the x. Okay, that's the distance. Now, also, distance equals rate times time. And I bring that up because they say how much time, r is going to be the amount of time that he spends running from that point. So I'm going to first write it as t, then I'll turn it into an r, because I already have an r that I want to use here. So I don't like that they're using r for time, and I'm using r for rate. Because his distance is going to be 20 minus x. Distance is 20 minus x. My r for this, temporarily, for rate, is 6.4 meters per second. Okay? So distance, I really don't like that they're using r. Distance equals rate times time. So time equals 20 minus x over 6.4. or now that I use their actual r equals 20. What did they say in terms of x? 20 minus x over 6.4. 20 minus x over 6.4. And I generally don't like decimals in my calculations. I could multiply everything by 10 and make it 200 minus 10x over 64 and find a way to reduce. That's fine. I could find something with that. For now, I'm just going to leave it like that. I think it uses the number 6.4, stuff like that. I feel bad using the r thing, like I said, but that was them using the rate. So that's what I have for his running speed in terms of x. It's based on whatever x is that we can figure out what his overall rate, what his time, excuse me, that's time. How long it would take based off his rate and stuff like that. Okay, Elvis swims at a speed of 0.9 meters per second. Write a function s, at least it's not r, in terms of x that represents the time he spends swimming from point D to point B. Now, as far as that goes, BD is the distance that he swims. That is, using Pythagorean theorem, this is a squared plus b squared equals c squared. So BD squared is 12 squared plus x squared. 12 squared plus x squared. I should put x first. Let's do this. X squared. Let's see. And that we'll call this a new distance. Distance equals, because that's the one we're talking about, x squared plus 144. So distance is the square root of x squared plus 144. So we have that set up. That does not equal x plus 12. That's not how square roots work. I hope throughout anything you've done, whether it was this chapter or being in IM3, now for my 1 and 2, that you stop doing that. Anyway, there's our distance. Distance equals rate times time. His rate, in this case, is 0.9 meters per second. So for distance equals rate times time, we're going to say distance equals rate times time. So time is square root of x squared plus 144 over 0.9. And, once again, I feel like we can do more with this to not make it look like a fraction thing. But this will be s. S equals plus 144 over 0.9. So we have two different equations. This time based off that x distance, and then this time based off that x distance. This is running speed and swimming speed. I know why they have r and s there for running and swimming. I just don't like that r is also a rate. Okay, part B. Write a function t. Oh, great. T is what I would use for time. In terms of x that represents the total time Elvis spends traveling from point A to point B. Well, times add together. So t, and I'll call these x, t of x equals r of x plus s of x, which means your running time plus your swimming time. So now I don't know if we're supposed to try and simplify these. I can go for a common denominator, but 20 minus x over 6.4 plus, only nothing will combine, x squared plus 144 over 0.9. Oh, common denominator of those two would be kind of tricky to talk about. So maybe if you want to, we can come up with something. This is currently a version. It's rough around the edges, but we can do it. 9 and 64 is least common multiple, or 9 and 32? 9 and 32 don't have a low least common multiple. I think you got to do times 32 for that. So I'll leave it like that. If they say do a simplified version, that I can work off that as well. For now, that just looks good. All right. Part C, use a graphing calculator to graph t. Find the value of x that minimizes t. Explain the meaning of this value. So I'm sure with the square root thing going on with the negative x, I'm sure it's going to do something that kind of decreases it. By the way, for domain, let's talk some domain stuff. Not because of the square root, but because x can't be more. X has to be less than or equal to 20 and greater than or equal to 0. Okay, let's just talk domain right there. If x is negative, then we're going out that way. I guess that's not impossible, but the dog wouldn't actually run farther and then go that way. And same thing here. The dog wouldn't go run backwards to go swim out farther like that either. So with that domain, I'll make sure that that's my window range of my graph. In case the graph does other things where it lowers, let's stick with that. So let's go to the graphing calculator. Let's type that in. We're going to have 20 minus x. The problem's nice. I just didn't like that r was used in that case. Over 6.4 plus, and this is square root of x squared plus 144. R divided by 0.9. I think I wrote that right. Let's go window. Oh yeah, I had to use this window for an earlier problem. 0 to 20, and What kind of times are we talking about? Probably something small. Let's go 0 to 10 and see what's going on. Oh, wait, hold on. This is for y, right? Oh, there's nothing on that graph. Hold on. 20 minus x over 6.4 plus square root of x squared is 1. Okay, I don't actually know. Hold on. This is y. What are we talking about for y? Y is what? Total time? Oh, it's going to take more than 10 seconds probably. Let's go to 100 seconds and just see what this dog's doing. They got to swim. Okay, so we're seeing that curve. Looks like I can reduce what I'm looking at there, but x kind of has to be between 0 to 20 for me based on what we're doing. So I think it's the y-intercept that'll be it, but we don't know the y-intercept based off our equation. Let's reduce it to about 30. It looks like we're seeing it more like that. Okay, the minimum's probably at that value right there, it looks like, but we got it. Well, actually, I don't know for sure. We don't know for sure that it's not bottoming out and doing something like that. So here's what we're going to do. We're going to say minimum. And we're going to go from 0 to 20, and ask the calculator. Let's guess anywhere around there from 0 to 20. What does it say? At x equals 0? No, they say at x equals 1.7. So that does bottom out at something that's not that thing. So, okay, it's not at a right angle. In order for the dog to optimize, and I don't know how much I want to talk about this thing here, but x is 1.7. This is meters for that part. You know, the optimization of this is such that, you know, okay, it's fast. The dog runs faster. Elvis runs faster than he swims. But if you don't cut it off at a certain angle, that, you know, that swimming time, although slower, is a shorter distance here than it is there. So there's this optimum level. That's why I like the question. There's an optimization. It's not that far off that the dog should be here to reduce the amount of time, which is there. If the dog started from here and started swimming, even though that's less distance than this is, right? You didn't get to take advantage of running. And if you go all the way over, you didn't take advantage of the shorter distance despite the speed or whatever. So it's a little bit less, around 1.7 meters. That's just the idea. So I like that version of what they're doing with that. I like them thinking in those terms. Obviously, the what do you call it? Obviously, the calculator did all this stuff for us. Oh, it says explain the meaning of the value. That's what it was. Sorry. Yeah, here, let me say more from this then. 20 minus 1.7 is the distance the dog's going to run on land. So that's going to be 18.3 meters running on land. And then swimming, we got to do square root of 1.7 squared plus 144. This is the dog's swimming distance. I got to still calculate that one. It's going to be a little more than 12, but square root of 1.7 squared plus 144, 12.12, I'll say 12.1, 12.1 meters swimming to reduce or minimize overall time. So what's the total? Oh, what was the total? Let's go back. I had to compute that last one. The total was, shoot, I didn't get the minimum. 16.3, and remember that's seconds. 16.3 seconds total. Okay. All right. And that's it. Guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. It seemed like a shorter video as a whole, sort of. It kind of got longer in the beginning, actually, compared to the end. We have one more section to go. I believe it's on inverses of functions, and what we learned in this portion here is going to be crucial to that. Thank you. Take care. I will see you in the next one.